address the next subject on technology and market involving for carbon fiber designer composites. Doctor?
Thank you. Till now we heard a lot about bulk carbon fiber in tons, and the product would be very big in size, and everything was based on how much it costs per weight and the energy used and so on. So I'm going to take a different twist to the whole thing. And what I'm going to cover is what's called designer composites for even a different market, but I'm going to show you applicable with one example to other markets as well. Is the right one? The technology overview that I'm going to cover will have some basics on carbon fiber that's used in cooling applications or thermal management applications as an example. And it's not limited to microfibers. We can use it for nanofibers also. Extend the same principles to nanofibers as well, or nanomaterial embedded in microfibers. And the application is a designer version where the conductivity expressed in watts per meter Kelvin is not same in all directions. They are different in different directions, X, Y, and Z. The demand is that there's a lot in electronics. If you look at microprocessors, if you look at any mobile devices, including mobile devices, the heat density is increasing. In a sense, typically a microprocessor is 1 centimeter by 1 centimeter square. It used to dissipate, once upon a time 60 watts, then it became 80 watts and 100 watts for the same area, because more and more processing is done, higher speed, etc., etc. So the heat density increases. In addition, the heat density is one important issue that we have to solve. Second thing is that there will be many hot spots. It just is at 1 centimeter square as an example in a microprocessor. And you cannot use the old-fashioned aluminum or copper that's normally used. And aluminum is cheaper, so aluminum used for large heat dissipation. Copper is more expensive. It's 10 times more expensive depending on what size and what volume you use. And so that's the most everyone has done. And I'm going to get into thermal interface material and so on. I'm going to get into details of that. Whereas anything that is non-isotropic, built from a designer perspective, with different properties in X, Y, and Z directions, will have some additional value. And this equation that you already know, and in the heat dissipation, and it depends on the area, it depends on the their length, it depends on the thermal properties of the material that you're using. And I'm not going to get into much of that. Okay. Now I'm going to take an example. I'm taking an example of this is a heat sink, and that is the microprocessor or any chip that's being cooled. Currently what happens is we are using aluminum most of the time, and then films will be there to dissipate further into the height. And between the microprocessor or any computer chip, there's a packaging that's around it, and from the packaging there's a little thermal interface material that is put in. There are two types of thermal interface materials. one inside the packaging between the microprocessor and the package, and then outside the package, which is a different thermal interface material. Traditionally, they call it thermal interface material or TIM, number 1, inside, number 2, outside. And I'm not covering that portion, I'm trying to take only the heat sink part. And what happens is the heat gets, if this is a copper or aluminum or any other metal like that, the dissipation does not go towards the end of it, it only goes towards that. Because the heat dissipates, in 3 dimensions. In this case, it's only hemispherical dissipation, heat spreading. And so, what happens is because of that, the heat is not reaching here and getting dissipated. The heat sinks at the end fields are not helpful, and the heat sink here is not helpful. And by the time it spreads this, because this being there, it does not help. By the time it has to go up, it has to go on the lateral side also, and it's not convenient. It doesn't cool back, even though it's being used. Now I will take a different one, and what we would be using is a material with anisotropic. I'm going to tell you how to build it, but I'm going to tell you the impact. If it is done, then we can have heat being dispersed or dissipated in the X and Y direction very well to the end, and then the heat sinks can pick up the heat, and then you can dissipate the heat through fan or whatever, even liquid cooling in the fan. And if this could be achieved, it would be a great advantage. That is, Kz is lower than Kx, even is what you need to have, or Ky, if you take the other side of it, Ky should be much better than Kz for it to have. But the same, which cannot be done using metals like aluminum and copper. And now, if you look at the same heat spreading, and this is how the heat spreads. If you take heat flux profile for isotropic material, like that. Whereas if we use an anisotropic material composite, it will spread this way. It is oblique in terms of how it spreads. That's the advantage we would get if we did that. And that is the base plate of any heat dissipation material, not necessarily limited to heat. It can be used inside the packaging as well, same principles. And if we use a designer thermal material, the heat spreading is even compared to the other one, which is not as good in terms of heat spreading, in all the directions. And this requires controlled manufacturing processes and using anisotropic material. Those are the two important parts. And a matrix is created, which is a designer matrix, and the different properties are used for X, Y, and Z planes, depending on how we are trying to dissipate, what is the heat that's being dissipated. And at the same time, I'm going to give you even much more intense. The microprocessors are becoming 200 watts, 300 watts per centimeter square being dissipated. And if you take solar, which is called concentrated photovoltaic, that you may be familiar with, what you normally see on solar rooftops is the simple crystalline silicon material efficiency compared to 17 or 18% efficiency. The triple junction, as it's called in solar, produces 43-44% already has been proved. Number one, efficiency goes up, and what people do is concentrate solar sun into a smaller area to save the photovoltaic material. And when you concentrate, when you go up to 100 concentrations, 200 concentration, the heat is quite a lot falling on the photovoltaic cell. And people have given up after 300, 400 concentrations because the heat is so high that you have to do liquid cooling and so on and so forth. And so using what I'm talking about, material, we have demonstrated going up to 2,000 cell concentrations. 2,000 cell concentration, just to give you an idea how much heat is being generated. If you put a solar cell and you don't cool it, and at the 2,000 concentration, it evaporates right away. It's that hot at the noon sun and so on. And we are able to cool that down to 6 degrees to 10 degrees above the ambient using this technology as well. Just to give you an idea, it is doable. And I'm going to talk about a multi-layered process as well, manufacturing process. And the way we would do is that we would have different, this is one plane where you see the carbon fibers there going this way, and the heat spreads in this direction. And if you want another one to spread in this direction, you can do, you can have multiple layers. You are creating a designer composite material with multiple layers, depending on how you want to move the heat. This is an example of either you can move the X direction or Y direction or Z direction, and this becomes a Z if you just flip it. And the way it is done is that, depending on how you want to move, and that's the matrix material that we would have, right? And then that's the X plane, and that's the Y plane, and that is Z plane. And depending how you put them together, then the heat can be spread, X, Y, or Z, because the carbon fiber in this case that we would use has very high thermal conductivity in the fiber direction, and very poor conductivity comparatively in the diameter direction or thickness direction. Let me give you some comparisons in real life. And thermal conductivity of copper, which is the best in electronic industry that's used, it's about 400 watts per meter Kelvin. And if you use a carbon fiber, a pitch carbon fiber, and the conductivity is about 800 and above, depending on how you make it. And so automatically you get a lot more in terms of thermal conductivity in that fiber direction. That's what we use in this case. And these are all carbon fibers. That's carbon fiber in the Z direction, X direction, Y direction. I'm just giving an example, not that this is the only way to do the metrics. It depends how you want to do the metrics. And now you go back to this, so you have to create multiple of these, and whichever way you want to pile them up and put them together, you can do it accordingly. That's the principle. And as I was telling you, the carbon fiber in this direction